It was fluid mechanics problems and a radius gyration.
That's what it was.
All right, let's get started. So I'm just going to jump right into structural design land. I'll show you a little bit about the review. So in a nutshell, we're looking at two topics on the exam. We're looking at concrete design and we're looking at steel design. Now, I'm going to say a couple things about these topics and then we'll get right into it. First off, let's talk about concrete design. When it comes to concrete design, the stuff that you get on the exam is orders of magnitude, I would say, simpler than what we did in class. In other words, no T-beams, no doubly reinforced sections, nothing out there. I don't really think you're going to have to deal with slab design. Development length, I really don't think you're going to have to deal with that. Really, it's just moment, shear, and columns. Okay. I have three problems for you to look at, and honestly, the first problem is a little bit of concrete design, but it's a little bit of just general structural analysis and LRFD load combos, 1.2 dead, that's 1.6 live. So it's a little generic. The other two, the shear and the column ones, are pretty basic because it's really about what you're going to get on the exam. For steel design, I want to say this about steel design. So if you want to talk about what types of problems you're going to get on the exam with steel, for beams and columns, probably you're going to have design problems. For tension members, probably analysis. In other words, you probably aren't going to have to design a tension member, and you might have a bolted connection, you might have a welded connection, but I don't think it's as prevalent or possible as a beam column or a beam design problem or a column design problem. And the reason I say that is look at the manual. If you look at the manual, the reference manual, all of the resources that you've been given in the manual all point to beam design and column design. And I'll show you that real quick because you'll be familiar with some of this. So I'm looking at the manual and I'm at the civil engineering section. So we're going to go past geotech, retaining walls. Now we're in structures land. So this is structural analysis. Most of this is stuff you really won't have to deal with except for maybe this. Y'all should remember that, unit load, virtual work. Here's the one for trusses, so little f, and then this, which is big F, L over DA, so that's just sort of how they rewrote that. Classification of structures, which is not really that big of a deal. Now we probably are starting to get into stuff that's a little bit more familiar, live load reduction, load combos, and now we're into concrete design. When you look at concrete design, for those of you who had that course, what you'll see is, first off, the notation. If you remember in concrete design, we were pretty hyper aware, if you will, of what symbols we were using for what dimensions. Like, for instance, when I used the dimension D, I didn't just throw that around flippantly. D always meant something. It was from the top of the beam to the center of the tensile reinforcement. D prime was the top of the beam to the center of the compressive reinforcement. Remember that? Then we had BW, HF, and all of that stuff. Like the definition of beta 1 and all of these are all standard terms in concrete design, and they're all sort of defined out. You've got your rebar sizes, typical patterns, and then if you look at the formulas that you're provided, the only thing that you're provided for beams, if you will, is, so we have our resistance factors, and then this is it for beams, ASFYD minus A over 2, and that's just a rectangular beam with rebar at the bottom. That's it. So the concrete design stuff, again, it's pretty simple. Nothing on design. You may have to use one of these. I don't have an example problem on this, but you might have to use one of these. Remember these? These are the PM curves, beam column interaction charts. So if you have a column that's got an eccentric load, pretty straightforward. But let me show you the steel design stuff. So for those of you that have had steel design, for those of you that have had steel design, so one of the first things you're going to see is the provisions on beams. So we have our plastic moment definition, we got CB, remember CB, that's our moment gradient modifier, so that accounts for non-uniform bending across the section. We have our column design formulas. Here's some shortcuts on CB. Here's some formulas for tension members. So remember, the net area equals the gross area minus the area loss due to bolt holes plus the presence of any stagger factors, right? Pop quiz. If you, let's see if y'all remember this from steel design. If you have a bolt diameter, how much do you add to that bolt diameter to get the hole diameter? If you're looking at tension members. An eighth, exactly right. You add a 16th to account for damage to the section, and a 16th for direction tolerance. In other words, you actually drill the hole a little larger than the diameter of the bolt, but we end up also adding another 16th to account for loss. Now the manual does provide you some basic section properties for some W shapes, some the area, the depth, the web thickness, flange dimensions, some flexural properties, you know, I and radius of gyration. Y'all remember that. Now, this table is your ZX chart. These are your ZX tables. So remember, we use these for beam design. So, pop quiz. When you have a group of sections and the top row is bolded, what does that mean? What's that? It's the lightest section within that group. So, for instance, if you look at this second group, the W21 by 55 is the lightest of everything in this group. And that's its ZX value. These are its anchor points, MP and MR. That's the slope of that linear portion of the LTB region. These are your other anchor points, moment of inertia, and shear capacity. Let's see what else. Remember these? Anybody remember these? So what do you do with these? So if you're trying to determine beam design, you go on the x-axis with your unbraced length, the y-axis with your available moment capacity. Find that point, and then which direction do I look to find a usable shape? Up and to the right. And then where do I stop? The first solid line, because the first solid line is the most economical within that given region. Here's our K values. So for columns, these are the ones for single columns. This is for columns and frames. More often than not, you're going to use the one on the right. That's the moment frame alignment chart. And then we have the KL over R tables. Probably aren't going to use that all that much, but you will use these. So if you go on, here's your length with respect to the least radius of gyration. Here's your W shape. And these are the compressive capacities. So remember we would go into the table with either KL in the Y direction or KL in the X direction divided by RX over RY. For those of you who remember that from steel design, that's this table. So just by looking at the manual, you can see that the manual places a pretty heavy emphasis on, when it comes to steel design, on beams and columns, on the stuff that we did near the end of the semester. For concrete design, it's really the simple stuff throughout the course. So that's really what I focused on. I got 6 problems we're going to do. 3 of them are concrete designs. I got a concrete beam for moment, concrete beam for shear, and I have a column. And then for steel, I have a column, a beam, and a tension member. That's what we're going to do. Yes, sir.
So aside from like conceptual stuff and the stuff they give us in the actual FE reference book, do we need to know anything from the steel manual besides that? Something that you would recommend us to
memorize? Yeah. No, not really. When it comes to like memorization for steel design and concrete design, really not that much. I mean, it might behoove you to remember what E is. And I would also say that while it's not listed in the manual, I would maybe try and memorize some very, very basic structural analysis shortcuts. For instance, if I have a simply supported beam with a uniformly distributed load, what is the maximum moment? WL squared over 8. And so those types of things I would try and memorize. Other than that, really no. All of the concrete design formulas, the steel design formulas, you know, like for inelastic buckling, you know, 0.658 raised to the, you know, FY over FE all times FY, you're not going to have to memorize that. It's all in the manual. So. Sound good? All right, let's get to it. Now I'm going to go ahead and tell you this is a long problem, but it's a long problem. So to be clear, this, I'm sure after the end of this problem, are they going to give us something like this on the exam? Probably not. This problem is really meant more to shake the rust off, if you will, you know, and get back into the world of structural engineering. So I have a 10-foot long beam with a cross section like this, a samurai sword or a lightsaber through the section, and I have a rectangular beam. It's 12 inches wide. It has an effective depth of 15 inches. Now notice that the total height of the beam hasn't been given, but honestly that really doesn't matter unless you need the self-weight of the beam. But we have a uniformly distributed surface dead load of 5 pounds per foot. That's a really light load, and you could probably neglect it, but we're going to consider it just to make sure that we remember how to do the math. We have a concentrated service live load at midspan, so a point load right in the middle. If we have an FC prime of 3,000 psi and a yield stress of the steel of 40,000 psi, what is most nearly the maximum allowable live load that the beam can withstand using LRFD? So there's going to be a lot to this problem, so I guess brace yourself. Brace yourself. I'm such a bored guy. All right, so here's the problem. Let's see what we can figure out. All right. Now, one of the most fundamental things that you need to keep in mind with structural engineering is that we always look at this from two sides of the equation. On one side we have the loads, and on another side we have the resistances. Now since we're dealing with concrete design, I'm going to start with the resistance. And so by resistance, what I mean is what is VMN. Okay, so let's see if we remember what that means. So MN is our nominal flexural capacity adjusted by our strength reduction factor phi, right? So there's two things we need to compute. We need to compute the nominal moment, and we need to compute the strength resistance factor. Now I printed off the solution, but I just realized about 2.5 seconds ago that I forgot it, so I'm going to need y'all's help with calculations, but you should have calculators as many of you do. So let's start off with nominal moment capacity. So let's see if this starts shaking the rust off. So I have a beam that's B wide, that has an effective depth of D, and I got some steel here. That's AS, right? So what can I do? Well, first off, I have the strain profile, right? And what do I assume with the strain? I assume that plane sections remain plane, so that means that my strain profile is linear. So it goes, that's maybe something about like that. That's good enough. So what do we know? We know that this point here, that's the strain in the steel, right? That's the strain in the concrete. Quiz. Anybody remember what the maximum usable strain that we assume for concrete is? 0.003. We always assume that is a constant value. So 0.003, and then this dimension here, we call that dimension C, right? So C is the distance from the top of the beam to where the neutral axis is, where there is zero strain, okay? Well, if I look at this from a stress perspective, what I do is if we're looking at the ultimate stage, I assume that none of the concrete in tension is experiencing, it's all cracked, it's gone. Concrete in tension like it's cracked. So on the bottom, all I have is a single tensile force where the rebar is, and as for the compression, I propose that it looks something like that. Remember, concrete is a very nonlinear material. So to be clear, that dimension is C, right? Okay, so if that dimension is C, and I've got this nonlinear stress-strain curve, I'm an engineer, I don't like dealing with calculus, I don't like dealing with nonlinear, so I'm going to take this and I'm going to idealize it as a stress block that is AD. So remember, A is the depth of the stress block, and that depth is different than the depth to the neutral axis. Remember, we relate A to C with some, what do we relate? What's missing here? A equals something times C. Theta 1, yep. Theta 1 times C. Okay? And then, how much stress is there? Remember, what's our maximum usable stress that we assume for concrete? It's not FC prime, it's something else. We assume that the concrete achieves a maximum stress in this stress block of 0.85 FC prime. Remember that? So 0.85 FC prime, and then our tension is the area of steel times Fy, right? We assume that the steel has yielded. In fact, it's more than just assuming the steel is yielded. We have conditions that it must yield. Because remember we had some checks that the beam had to meet beyond just its capacity. There was a limit on the strain in the steel. Remember, the strain in the steel had to be bigger than a certain value. Do you remember what that was? Like, we would compute the capacity, and then we would have to check and make sure that we provided the steel. We had to have at least the minimum amount of reinforcement. So remember, AS had to be greater than AS meant, but then the strain had to be greater than a certain value. It was not 0.005, it was 0.004. Now, the 0.005 is going to come up here in a second, so that's easy to forget. That's totally fine. Okay, now, let me walk you through this. So, FC prime for this problem is 3 KSI, and Fy is 40 KSI. So, how do we go about a beam analysis problem? Well, we start by looking at equilibrium. In other words, all of the compressive forces have to equal all the tensile forces. And so, what does that mean? Well, what are the tensile forces inside this beam at its ultimate at its ultimate stage? Well, it's just the tensile force in the rebar. It's just AS Fy. What about the compressive force? Well, the compressive force is what we get out of this. So I propose it's 0.85 FC prime times A times what? Well, we're getting to that. Remember, it's 0.85 FC prime times A times B. In other words, remember the stress block kind of looks like this. Oh, I did that wrong. So here's the beam in 3 dimensions, right? And so the stress block kind of looks like this. My 3-dimensional art is not very good today. Right, so this this dimension is A. This dimension is B. And then this dimension here is 0.85 FC prime. So the total amount of compressive force is 0.85 FC prime times the area of that block. So it's AB. Is everybody remembering that? So if we look at this equation, what do we not know?
A.
We don't know A. Exactly right. That's the depth of the stress block. So A is ASFY divided by 0.85 FC prime B. And so, let's see. What do we know? Well, what's going on with the area of steel? There are 3 number 9s. Everybody remember what the cross-sectional area of a number 9 is?
1.
1 square inch. That's what a number 9 is. It's a rebar that has an area of 1 square inch. So 3 number 9s have an area of 3 square inches. This is 60 KSI, 0.85, 3 KSI. Oh, you're right, you're right. And then B was what, 12 inches?
Yeah.
Yeah, it's 12 inches. And so that equals what? Okay, so therefore our nominal moment capacity, and remember how we develop our nominal moment capacity. Remember, what is moment? It's just a force times a distance, right? So remember, we have a force here and a force here, so it's just the force times that moment arm, right? Remember, if you have 2 forces going like that, that force couple is just, F times C. And so the force, well, which one do I use? Do I use 0.85 FC prime AB, or do I use ASFY? Well, the short answer is ASFY. The long answer is it really doesn't matter because the 2 forces are equal. So be lazy and use the section or the force that has 2 terms versus the one that has 4. So just use ASFY. And then the moment arm, how far is it between these 2 forces? Well, we go up here. This dimension is A. So the center of that resultant force is right here. So how far is it from here to there? What is that dimension? Well, it's D minus A over 2, right? So that was a go-to formula for a lot of our simple beam design problems. So this is 3, 40. What was D? Minus 3. 2 inches over 2 equals. Say it again. 1564.7. Do I have a second on that? Awesome. Now, what are the units? What? Inch kips. Because we've got KSIs and inches. So this is inch kips. What about in foot kips? How do I convert from inch kips to foot kips? It's simple. Just divide by 12. Yeah. 130.39. Did I get that right? All right. Foot kips. All right. So far, so good? that's what I wanted to hear. I was hoping somebody would say 0.9, so I would do that. Remember, phi depends. What does it depend on? The strain in the tensile reinforcement. Yeah. So you said 0.005. If the strain in the tensile reinforcement is larger than 0.005, then phi is 0.9. Otherwise, there's that linear fit. So we got to figure that out. So we'll say strength reduction factor. And for you folks who had steel, you know, the phi value here serves the same purpose. It's just in concrete design we have to compute it, whereas in steel design we would just look it up. So the first thing we have to compute is that neutral axis depth C. So that neutral axis depth C is determined by that expression, which is A over beta 1. So 3.922 inches over. Ooh. What is beta 1? First off, what do we look at if we want to try and figure out beta 1? What value do we pay attention to? Like how do we determine what beta 1 is? It depends on what? What's that? It depends on FC prime. Exactly right. So remember, there's always manual. So remember, beta 1 ranges anywhere between 0.85 and 0.65. And remember, it's sort of a measure of your ductility. So if you have really, really high compressive strengths, your beta 1 value goes down. Now we have a really low compressive strength on this problem because our FC prime is only 3 KSI. Now if you put it, or 3,000, so if you put in 3,000 here, you could compute it. What you'll end up finding is that beta 1 is 0.85. Anytime that your FC prime is 4,000 PSI or less, beta 1 is 0.85. And that equals what? Now, does anybody remember how to find the strain in the seal? There's a formula, but let's say you forgot the formula. What'd you say? Everybody remember? You can just use similar triangles. Remember, 0.003 is to that as this is to that, right? So 0.003 is to C. Hi. So 0.003 is to C as epsilon sub T is to D minus C, right? Y'all remember that? So 0.003 D minus C over C, right? That's D. So 0.003, 15 inches minus 4.61 inches over 4.61 inches. And that equals what? 0.0068. 0.0068. Do I have a second on that? Now, looking at that value, what is phi? It's 0.9. Anytime that strain is larger than 0.005, phi is 0.9. So if phi is 0.9, what is phi mn? It's 0.9 times, what y'all give me? 130.39? We'll just do that. That's the nice thing about the FE, but we should be close enough. So. Are we good? That's not too bad. Yes?
In the manual for the equation for Untitled Chapter, they have like dt minus c. Is that just the difference to this, like our what we call our v?
Oh, yeah. That's a good question. So the difference between the d sub t and whatnot is if you have multiple layers of steel, whether or not you're going to the center or to the very, very, very bottom. What the strain check here is saying is that you go to the very, very bottom. So that's the d sub t, to the very tippy, not tippy top, but tippy bottom. That makes sense. But that's all I'm about. But in all seriousness, I would wager that your likelihood of having to deal with a beam that has multiple layers of steel is probably pretty low. So it's the same. That's a good question.
When that happens, then we assume it to be like in between.
For the D value, yes. For the moment arm, yes. But for the strain check, you would technically go to the very bottom. But again, I don't think you're going to have to worry about that on the exam. Does that sound good? Okay. Again, like I said, this is a problem that you're probably not going to get on the exam because it's meant to be a review problem, not a typical exam problem. Okay. We're not done because we have to look at the other end of the equation. The other end of the equation is the loads. The problem asks, what is the maximum service live load that I can put in the middle of this beam so that it doesn't fail, okay? So now let's look at the loads, all right? All right? So let's start off looking at dead load. Let's look at dead load over here, and we'll look at live load here. Okay, so let's look at dead load and live load. Now the dead load on this beam is a uniformly distributed load. It's really small, it's only 5 pounds per foot. If you have a beam that has 5 pounds per foot, in reality, what do you think you can do for a problem like this? Just ignore it. We're not going to ignore it in here, not because I'm trying to make the problem more complicated, but this is a review. I'm trying to make sure that everybody remembers how to do this stuff. Okay? So, yeah, 5 pounds per foot. So, we have a distributed dead load of 5 pounds per foot, or 0.005 kips per foot. And the length of this beam is, hold on, 10 feet. So what's the dead load moment? W L squared over 8. So 0.005 kips per foot times 10 feet squared, don't forget the squared, over 8, which is what? Say it again. Foot kips. All right, that's easy. Now the live load, I have a beam that has a concentrated load at midspan. right? So, do y'all remember the formula for the maximum moment? It's okay if you don't. It's PL over 4, that's exactly correct. But if you don't remember, that's fine because you can very easily derive it. That's L over 2, that's L over 2. So, actually, let me leave the subscripts off because that's going to get a little confusing. So if that's P, that makes that P over 2. That makes that P over 2, right? So what's the shear diagram look like? So we start at 0. We go up to P over 2. Constant. Drop down. Negative P over 2. Over. Back up, right? Then we take the area under the shear diagram. So this rectangle is P over 2 tall and it's L over 2 wide. So it's PL over 4. This is positive PL over 4 minus PL over 4. So that's the shear diagram. The moment diagram, we start at 0. Constant shear means linear moment, PL over 4, linear back to 0. So therefore, ML is PL over 4, or PL times 2.5 feet. Did I go too fast on that? Everybody okay with that? Okay, so if you're all right on that, let's sort of summarize everything with this problem. So VMN is 117.4 foot kips. MD is 0.0625 foot kips, and then ML is some load, we don't know what that load is, times 2.5 feet. So since VMN has got to be bigger than our factored load, and what's our factored load? There we go. 1.2 times dead plus 1.6 times the live. So VMN has got to be greater than or equal to 1.2. Well, here, let's just do it like this. This is 117.4 foot kips. This is just solve for PL. What is PL? .33. So PL has got to be less than or equal to 29.33 kips. I know that was a long problem. It was meant to be a review to sort of get us, get the rust, shaken off in regards to LRFD, and I know there was some concrete design stuff in there, but there was also just some general structure stuff, like all this stuff about 1.2 dead plus 1.6 live sort of applies to everything. Any questions? Very good. All right. The problems from here on out get a lot shorter, I promise. All right. Let's look at problem number 2. So I have a singly reinforced concrete beam shown below. The values, I think, are a little more typical. 4,000 psi concrete, 60,000 psi steel. What is most nearly the ultimate shear capacity? So this problem, let me be clear, this is probably actually a little different than what we did in class, because we didn't really do many problems in class where I just asked you what the shear capacity was. Because the way that shear design worked in class, you could always, first off, does anybody remember what the shear capacity is a function of? It's a function of the VC and the VS, right? And so what would always happen is that, so VC is the shear capacity provided by the concrete. We would always have loads on the structure, and what we would find is that VC wasn't enough. It was never enough. That's why you put stirrups into the beam to resist that shear force. Well, so as a result, we never really computed the shear capacity directly. But I think you'll find it's a very, very simple process. It's a very typical problem that you could get on the exam, and I don't want it to trip you up. All right. So, first off, VBN is computed as VBC plus VBS, right? Now, for bending, you have to compute your phi value. For shear, you look it up. Does anybody remember what the phi value for shear is? 0.75. Exactly right. Okay. So let's see if we can compute a couple of these values. Let's start off with VC. Anybody remember how to compute VC? Anybody remember the formula? You don't have to remember the formula, it's in the name. 2 lambda BD square root of FC prime. There you go. So let's chug that out. 2, now lambda. What was lambda? Anybody remember what lambda was?
Factor for concrete material.
It's the lightweight aggregate factor, right? Whenever you're dealing with lightweight concrete, you have a lambda value that's less than 1, right? So for normal weight concrete, this is 1. All right, B and D are 18 and 33 inches. Respectively. Square root of 4 KSI. Right. You put in when you have a square root of FC prime, you put in PSI. You get out PSI. I see some folks like, I remember that. Yes, sir.
Why in the manual is the lambda value not in the formula for BC?
That's a great question. Does anybody have an answer why you think that is? Because you're never going to have a lightweight aggregate factor on the exam. I'm serious. I know that sounds like a cop-out answer, but it's really the truth. All right, so first off, let's compute the value here, the number.
75,135.
75,135. Do I have a second on the value?
Yeah. It's 0.72.
I'll just see here. Now, what are the units?
PSI.
Pounds. Pounds. Remember, you put in PSI, you get out PSI, but it's multiplied by inches, multiplied by inches. So this is 75.14 kips. All right. Now that's VC. What about VS? What's the formula for VS? All right. Now, does anybody remember why the formula is D over S? Remember, here's a concrete beam. right? So here's its support, goes like that. And so, God, that is that's better. So here's the concrete beam, right? And so our stirrups sort of go like that. Behavioral question. When concrete cracks in shear, it cracks at what angle?
45.
There we go. So it's going to crack about like that, right? So the D over S is basically a measure of how many stirrups will cross a crack. So we say the crack is D tall, so we want to know how many stirrups. So D over S is the number of stirrups per crack. All right? Now, let's see. So let's fill in some values. Okay, what's the stirrup spacing? 12 here, there we go. So 12 inches. The D value is 33 inches. FYT, that's 60 KSI. Now, let's see if we remember this. I got number 3 stirrups that are U-shaped. So the area of a single number 3 is 0.11. What value do I use for AB? 0.22. Because if I samurai sword or lightsaber through the middle of the beam, how many bars am I cutting through? 1, 2. So 0.22 square inches. And so, what does that come out to be?
36.3.
36.3 kicks. Do I have a second on that? That's a beam that's rather lightly reinforced, I would say. So therefore, BVN is VC plus VS all times 0.75. Not too bad, right? Pretty simple. That is really the type of problem you would get on the exam. That's a FE exam problem for concrete if there ever was one. In terms of complexity, length, information given, what they would expect of you, perfect exam. Any questions? All right, one more concrete problem. Then we're in steel land. All right, I got a column. It's a square column. I got 8 number 9s, 16 inches by 16 inches, 4,000 PSI concrete, 60,000 PSI steel. What is most nearly the ultimate axial strength? VPN. Tie reinforcements are utilized. So I actually don't even think I need to break out the notebook, although I will, because I can probably do this one very, very quickly. All right. First off, does anybody remember what your phi value is for a column that's reinforced with ties? 0.65. How does that, like, there's 0.65 for tied columns, but what else? Spirally reinforced columns. And spirally reinforced columns have a phi value of what? 0.75. All right. Now, let's go to the manual. I'm on page 161. Keep in mind, it doesn't even list spirally reinforced columns, so I can tell you if you ever have to deal with those. Yes, that was my question. Yeah. All right, now, but I am going to ask you a behavioral question. So here's our formula, very, very plug and chug. What's that? Who remember? It's a 0.8. Oh. Man. Anybody remember why we put the 0.8 there? Reasons. No, it's not for buckling. Remember, this equation assumes that the load is dead perfectly right smack dab in the middle of the centroid. What if that load is kicked off over to the side? Remember, we cut our curve off a bit to account for accidental eccentricity, for the load being a little bit off center. So we reduce our usable capacity by a bit. That's what that's for. So. Oh, goodness. So there's our formula. So all I got to do is just plug and chug. So 0.8 times 0.65 times 0.85 times 4 KSI times, okay, AG minus AST. What's the gross area of this column? 16 squared. So 16 times 16 is 256. So 256 square inches minus, what's the area of the steel, the tensile reinforcement?
8 inches.
8 inches, because 8 number 9s. Plus 60 KSI, 8 square inches. D. Again, that is a very possible problem on the exam. Or maybe an extension of that is this column supports a flooring system that has an area of 500 square feet. So what's the maximum pressure load? So if it's 688 kips over 500 square feet, what's that pressure? You know, something like that. That's a very possible extension of that. Sound good? Ready to talk about some steel? Yes.
This, I remember, was it steel or was it concrete that went over tributary areas?
Concrete.
Concrete?
Yes.
Is there tributary stuff on there? Because that was kind of...
I tell you what, next week, so I have a problem. The lecture that we did last week in structural analysis, I pieced together a new recording that covered a tributary area problem that I did last year. But if you want, next week we've got time, I can do that tributary area problem because it covers that. It also covers live load reduction and all of that stuff. So we can do that next week if you'd like. I don't have a problem with that. So. But those are fair questions. Ready to do some steel? Let's do some steel. So I'll go ahead and tell you that I'm doing the steel design problems out of order from how we did them in class. So if you had concrete design, we did bending first, then we did shear, and then we did columns near the end of the semester. But I'm doing columns first here because it is really what you would see on the exam. So you steel design folks, let's see if you can remember some things about this. So from the choices below, what is the lightest wide flange shape that can resist a service dead load of 125 kips and a service live load of 200 kips using LRFD? For this column, take KX and KY to be 1 and L to be 15 feet. first off, of these choices, ignoring all this, which one's the lightest? D. Why are you saying that? The 40, right? Remember, the 12 is about how deep it is. The 40 tells pounds per foot, how heavy it is. So the smaller this number is, the lighter it is. Now, Kx and Ky. Kx and Ky are my effective length factors for column buckling. If Kx and Ky are the same, and the length is the same in the both directions, which axis governs my design? The strong axis or the weak axis? The weak axis, right? Remember, so what gets complicated is if I have a weak axis length that's 15 feet and a strong axis length that's 25 feet. Then I got to figure out what's going on, right? But because everything's the same, all I have to consider is KL along the y-axis is 1 times 15 feet, which is 15 feet. And then my factored load is 1.2 times 125 plus 1.6 times 200. Bless you. So what does that come out to be?
470.
470 kits. Give everybody a second on this. All right. I'll go ahead and tell you that steel design, much more than concrete design, you need to use the manual. Everything that I was doing with concrete design, you know, if you were to memorize the formulas, I'm not saying you have to, but if you were to memorize the formulas, you'd be fine. I mean, you'd be able to do concrete design without ever having to look at the manual, especially if you know some of your rebar areas, like the area of a number 9 is 1 square inch. That's another thing you might want to memorize with structures, the area of a number 9, because they're pretty common. Steel design, you really need to use the manual. So, let's see if y'all remember how to do this. So, here's steel design. Here's our section properties, CX tables, beam charts, K values, and then this. Now, I'll go ahead and tell you, this looks a lot different than it did in the manual. Remember, the one in the manual had the green numbers and it had the blue numbers. Which numbers did we use? The blue numbers, right? The blue numbers corresponded to LRFD, so we always use the blue numbers. This is just the blue numbers. The manual, that's another reason in steel design why I teach LRFD, because that's what they do on the exam. It's just LRFD. So, remember over here on the left, the effective length with respect to the least radius of gyration. So our KL was what, 15 feet?
Yeah.
So what we're going to do is go off of that row, right? So the KL is 15 feet. And then we're going to start looking for shapes that have an axial capacity of what? 470. Oh, I'm not going to do that. I'm not going to do that. So 470, maybe I'll use my pen. So we're looking at W12s. Why are we looking at W12s? Because that's what the problem was asking for, was W12s. So does the W12 by 40 work? The one over here? Let me zoom in a bit. Does the W12 by 40 work? It has a capacity of 280. What about the 45? What about the 50? What about the 53? There we go, because it has a capacity of 477, and the load is 470. So what is the answer to this problem? It's A. It's actually the heaviest section because it's the only one that has a capacity of 470 kits at a length of 15 feet. we think? Y'all remember that? Yes, sir.
For that last problem, whenever we solved for the total load, PU was 470, the chart, the other table, it says RFD VPN. I can't remember, PU or VPN, the same thing.
So no. PU is the load, the demand on the system. VPN is what it can supply. So you just need the VPN to be larger than what we computed. So think of what we computed as the limit, and then those are the other end of the expression. Sound good? All right. Let's take this problem in a bit. So I have a W24 by 55. It's to be used as a simply supported beam. The span length is 12 feet. It's going to support a uniformly distributed load. What is most nearly the design flexural capacity of the beam if only the ends are laterally supported? Okay, so let's see if we can make sense of this. Now this problem is making things a little simpler for you because CB equals 1. Okay. Now, we could redo this problem by considering a CB value larger than 1, and I'll show you how to do that here in a second, but for now, we're just going to keep that basic. So C sub B is 1. Let's see. So the length of this beam is 12 feet. What is LB? It's the distance between braces. So what is LB for this problem?
12 feet.
It's 12 feet. Because it's only braced at the ends. If there was a brace at midspan, what would the LB be? 6 feet. Remember, this is easy to mess up on the exam. There is a difference between the length of the beam and LB. LB is the distance between braces, okay? So make sure that you clearly are able to identify that difference. Now, a W24 by 55. All right, does everybody have all this info? Okay, let's go to the manual. I want to go here. Does everybody remember this table?
Yes.
Okay. So this is the ZX table, and we're looking at a 24 by 55. So I want to look at these properties. In fact, I'm feeling a little lazy, so I'm going to screen capture this. That there. Okay. Let's see if y'all are paying attention. What can you all tell me about PVN for steel, the shear capacity for steel beams? Anybody remember anything about that?
Don't have to worry about it.
You generally don't have to worry about it. Exactly right. When you look at steel beam design, particularly design of rolled shapes, in buildings, what you find is that the load is like 20 kips, but the capacity is like 251 kips. That's very common. I'm not saying ignore shear. I'm just saying it's generally not an influence on your design when you're looking in buildings. Bridges, that's a different story, but that's besides the point. Okay. Lateral torsional buckling. Remember there were 3 zones, right? Those zones are defined by these points right here, LP and LR, right? Remember, if your brace length is smaller than that, it's just going to be FYZX, right? Your VMP. If we're between these points, we've got that straight line fit. And if we're outside that, we're in that elastic buckling zone where the equation gets really funky. So we're definitely looking at zone 2, right? Because LB is 12 feet and it's definitely between LP and LR. So what I'll say is based on this and based on this, we are in zone 2, right? Now, if we're in zone 2, there's our capacity right here.
It only hits that equation. It doesn't have the one for 1 or 3.
What's that?
It doesn't have the one for 1 or 3.
You're exactly right. Well, what does that mean?
We're not going to get it.
There, see, man, I told you, it's a lot more. Again, that's what I'm saying. We covered way more than what they cover on the exam. All right.
I can't even find that. It's
160.
Sorry, did I go a little fast on that?
I'm just.
It's right here. It's on page 163 is the moment capacity. I need to turn that highlighter off because I'm highlighting stuff all over the place. What was I doing? Oh, sorry. Okay. So here's our equation. Now let's see if y'all remember this. When you have a pile of junk less than or equal to another pile of junk, what does that mean? In steel design. You're about to say something.
I mean, it can't be greater than that, but we're not just using MP.
No. Whenever you have an equation in steel design where it says the capacity equals this, less than or equal to this, remember it's a fancy way of just saying the minimum of those two quantities. Y'all remember that? So that's really what that means. So let's see. Let's see if we can rewrite this. So far, so good? Okay. Now, I'm going to sort of do this problem the way that I think you would do it on the exam, and here's why. If you recall in steel design, we had a shortcut way of getting around this formula. And the shortcut way of getting around this formula was to use this, the beam factor. And that beam factor is really just the slope of that line in the inelastic LTB range. Well, we don't have that formula. It's not provided. So I'm actually going to use this expression and just compute the stuff that I need. Okay? So let's take this equation. What don't I know right now? I've got LB, I've got LP, I've got LR, I've got FY. Let's start off with SX. Does anybody know what SX is for a W24 by 55? The beam factor, yes, but not the modified capacity using the beam factor. So how would we find SX for a W24 by 55? There you go.
114.
Right here, 114. See, they give you that information as well. So it's going to be in the manual, I promise. So we know that is 114 cubic inches. What about MP? Does Does anybody remember how to compute MP? I know they report a phi MP, so if you wanted, you could take that divided by 0.9, but this is more behavioral. Anybody remember how to compute MP? Fy CX. So that's 50 KSI times 134 cubic inches, and that equals what? Say it again?
6,700.
6,700 even?
Yep.
Is everybody with? Am I good?
Yeah.
So therefore, I'm getting a little sloppy here. Let me sort of clean this up. Therefore, MN is the minimum of, oh, I forgot my CB up here. Well, CB is 1, so it doesn't really matter. So MP is 6,700 inch kips, sorry, minus 6,700 inch kips minus 0.7 times 50 KSI times 114 cubic inches. I'm going to replace these with braces. Times, what was that, 12 feet minus 4.73 feet. 13.9 feet minus 4.73 feet. Or 6,700 inch tips. So it's the minimum of everything on the top, or 6,700. Go ahead and tell you it's not 6,700. The reason it's not this is because CB is 1. Remember what CB does. CB ups your capacity based on non-uniform bending. But I don't care what CB does, it can never be larger than MP. So does anybody have a value for that expression? I know it's long. Take your time. This is just a little heavy. $4,552. Do I have a second on that?
Yes.
Okay, that's, what's the units?
Inch kips.
Okay, divide that by 12.
379.
Well, I'll be golly gosh gee, that doesn't match any of the choices. Why?
Most nearly.
What's that?
Most nearly.
No, it's not most nearly.
Then multiply it. Well,
What's the problem asked for? The design flexural capacity. We computed the nominal flexural capacity. What's the phi value? 0.9. PMN is 0.9379. And what is that?
341.
That's a little better. There's probably some rounding issues there, but that's a little better. I have one more problem. It's a lot easier, because it's a lot more straightforward. But before I move on, does anybody have any questions? I've reviewed like 2 classes in an hour and a half. It's pretty good. All right. All right. When you do tension member problems on the exam, let me say a couple things about tension member problems on the exam. First, by and large, they will be analysis problems. If you are given a section that's not a wide flange, if it's an angle, channel, something like that, they have to give you the properties. Why? Because they're not in the reference manual. The only properties that are in the reference manual are there's that very small table of wide flanges. Okay? So that's something to keep in mind. And so as a result, it's actually very rare that you would have a tension member that's a wide flange. At least I think so. And the reason why is because remember your shear lag factor, you need the equivalent properties of that WT. Well, we don't have that, so that's a little bit of an issue to work out. I got a tension member. It is comprised of a 6x4 by 3/8 inch angle. It's grade 36 steel, so it's 36 KSI for the yield strength, 58 KSI for the tensile strength. It's shown below. I got 5 bolts that are 3/4 inches in diameter. What is most nearly the design axial capacity of the member? For the purposes of this problem, you may neglect block shear, and you may neglect everything with the bolts. So there are 2 limit states that we need to assess. Does anybody remember what those 2 limit states are? No, we can neglect block shear. All right. I give you a hint. All right, one of them is a synonym of icky.
Gross.
The gross section yielding. And then when you're playing basketball, at nothing but net.
Can't forget this now. Fraction.
Y'all remember that, right?
Yeah.
I know it's late, and I know it's getting dark. I know. We'll get through this quickly. Gross section yielding, net section fracture, right? So let's test y'all's memory banks. Which one's the easy one?
Gross section.
There we go. All right. So gross section yielding. So VPN is, what's phi for gross section yielding? What's that? Yep. 0.9, and then what else? 0.9, what's the capacity?
FYAG.
There we go. FYAG. So 0.9 times 36 KSI times, they gave us the AG, it's right here. It's 3.61 square inches. Somebody give me a value on that. We'll put that over here.
116.
Say it again.
It's about 117.
117 kips. Is that our, I mean, that's a choice. It very well could be our answer. It depends on what the VPN is for net section fraction. I have no idea what it is. We have to do the math. So let's look at net section fraction. Does anybody remember what the formula is? So first off, what's our phi value for net section fracture? So we take 0.75 times FU times what? AE, the effective net area. And how do we compute the effective net area? We need 2 quantities. We need the net area, and we need what? Well, yeah, I'm saying that there's 2 ultimate challenges. We need the net area, and we need the shear lag factor. I mean, you all are correct. I mean, we need to go through all that. So, but ultimately, that's our goal. Bringing it back, right? All right. What's that? Oh, we'll get there. We'll get there. All right. So let's deal with the net area first. All right. We have 3/4 inch diameter bolts. So the diameter of the hole is what? You add 1/8, right? Now that's a fair point. Remember, you add 1/8 when you're doing tension members, but you add 1/16 when you're looking at bolt bearing because you're looking at the physical dimensions of the hull. So remember that's a very valid thing to bring up. So this is 7/8. We have a thickness of what is it? What's the anchor? 3/8. Now, I see something with this bolted connection pattern that we're going to need to consider. We got staggered bolted patterns. We need a stagger factor, which means we need an S value and we need a G value. Let's start off with the G value. Does anybody remember which way you measure G? What's that? Yeah, perpendicular to the load. So the load's going this way, G is going to be 3 inches. The stagger factor is the diagonal, or that spacing this way, so the stagger is going to be 1.5. Right? Now, remember, when you're defining net area failure paths, you're going off of the lead line, right? So here's the tension member, so we're going off of all of the bolts that are along this path. And I propose that there are 2 paths that we need to consider. This one, that's close enough. This one, and that one, right? So we'll call this 2, call that 1. So for path 1, we'll say the gross area minus 1 bolt hole. How do we compute the area of 1 bolt hole? Say it again?
1 times the edge.
Well, 1 time, no, you're not quite. You're close. The diameter of the hole times what? The thickness, right? Remember, it's got to go through the plate. Remember, it's not pi over 4d squared, right? If you say that, that's wrong. So, DHT. So, 3.61 square inches minus 7/8 times 3/8. So that equals what? .28. Do I have a second on that?
Yes.
Path 2. How many bolt holes am I subtracting? 2. But I'm missing something. I gotta add a stagger factor. Remember, it's S squared over 4G times the thickness. So 3.61 square inches minus 2 plus, and so we have 1.5 squared times 3/8 over 4 times 3 inches. What we got? Yes, sir.
In the reference manual, for the net area staggered holes.
They don't, let me guess, they don't list the T.
No, it's on the outside, but it says DH plus 1/16 instead of 1/8.
That's a fair, you're exactly right. Now, what does it say for DH?
Oh, sure.
I don't like the way the manual does that. I really don't like that. Yeah, the manual says DH plus a 16th, but then dB plus a 16, so you're adding 16 twice. I really don't like that the manual does that. I wish they'd just keep it simple, but yeah. I don't like that. You're exactly, that's a very astute observation, Matt. That's correct. What do we got here for this? Anybody have an answer for me? 3.0 what? 2. 2. Do I have a second?
Yes.
Okay. Which one do I go with? It's smaller. If I'm yanking on this, it's going to fail along the worst case scenario, the path of least resistance. And so the path of least resistance is the path that uses the least area. Now, shear lag factor. Now let me make sure I'm clear on what the manual says. Okay. So, manual only lists that formula for angles. So 1 minus x bar over L. So U is 1 minus x bar. Remember, I like to write it like this because it adds some specificity to what the values mean. Remember, this is the connection eccentricity, this is the connection length. The connection eccentricity is the distance from the connected face to the centroid of the member. And usually for angles, you had to figure that out. It was either x bar or it was y bar, dependent upon which space was connected. For this problem, they just gave it to us. So it's just 1 minus, and then the fraction is, what was it? 0.933. Now the connection length. How long is this connection? Does anybody remember how that works? What's that? One of those three numbers? Now, remember, the connection length was the distance between the outermost bolt and the outermost bolt. So if you look at this diagram and you say 7.5 inches, that's wrong, okay? Because the 7.5 inches is saying, let me erase this. So it's saying if you start over here at the left end of the angle, that's 1, 2, 3, 4, 5. So it's saying each of those spaces are 1.5 inches. So, 1.5, 3, 4.5, 6, 7.5. Now my question to you is, how far is it from the outermost bolt to the outermost bolt?
6.
It's 6 inches, right? Because it's 7.5 inches from this outermost bolt to the edge of the angle. I don't care about that. I'm going from edge of bolt to edge of bolt, and that's 6 inches. Does that make sense? So that's something that could really easily trip you up on the exam. Make sure that you're aware of what that means.
Is that center to center, or is that?
Yes. It's center to center. That's a good question. What do we got here?
4, 8, 4, 4, 5.
So U is 0.845. So therefore, VPN is 0.75, 58 KSI, 3.02, 0.845. What is VPN? I have a second on that?
Yeah.
So going to the prop, wait. Really? did something, there's something wrong here, because if I remember correctly, I thought this value came out to be larger than 117, because I was a jerk and that was the answer, and we did all that work for nothing. But something didn't work out. I don't know. I will look at it and maybe post an updated solution on Blackboard or something this week, whenever I have time. But my main concern is, do you understand the concept? Okay, I know it's, okay, it was dark before, now it's really dark. Time change thing. That's all. Does anybody have any questions? Yes.
Are you going to put these lecture slides on Blackboard?
I will. I didn't get a chance to do it before class, but I will. I'll post that, and then I think I still need to post the structural analysis ones.
And the survey ones?
Did I not post the survey ones? I'm sorry. I'll post those. Okay. I'm slacking. I'm sorry. I thought I had handled that. I'll spend some time, maybe either tomorrow or Friday, on Blackboard, putting some love into this class to make sure everything's posted, except for the solutions quizzes that you've got coming up. Next week, we might chat a little bit about the project, because that, yeah, does kind of matter. And we'll sort of powwow about that. We don't really have any topics in here left to discuss for the exam, other than maybe like statics and dynamics and prop stats. I think that's it, right? So maybe chew on what you want to look at near the end. That's all I have, everybody. Really, that's all I got.